Okay, hello everybody. That's much allowed. I would like to introduce you today to magnetochemistry. And first of all, I would like to mention that this is not a scientific lecture. It is just an introduction into the basics. So in magnetochemistry, there are two very, very distinguished subdisciplines. That is the solid-state magnetism, and this is the molecule-based magnetism. So I will not talk today about solid-state magnetism. In molecular magnetism, there were also two subdisciplines. There's one on the right, which is more application-based. So there's molecule-based magnetic materials. And in this field, people are looking for real magnets. Real magnets, as in solid-state magnetism, where we have a long-range magnetic order below a Curie temperature. And there is a new phenomenon, single molecular magnets. These are not solid-state magnets. They have not a magnetic order, but they also have hysteresis as a real magnet. But this arises from a slow relaxation of the magnetization below a so-called locking temperature. I will not talk about this today, because today we want to go into the basics. And I will touch the paramagnetism, I will discuss mononuclear complexes, a little bit of zero splitting, and exchange coupling in polynuclear complexes. So first of all, let's start with a macroscopic sample. And if we put a macroscopic sample into a homogeneous magnetic field. So we have the field in this direction, we have the north pole and the south pole, and we have the magnetic field lines. The magnetic field is expressed by H. It's a vectorial thing. And here we have an induction, the magnetic induction. The magnetic induction is simply the amount of magnetic field lines through an area perpendicular to the direction. So the more field lines are here, the stronger is the induction. And this is the case for vacuum. There is nothing in the magnetic field. And now if you put in a macroscopic sample, there are two possibilities. One possibility is that, so this square here is the macroscopic sample, that the sample pushes the magnetic field lines outside. So that means that we have inside the sample a smaller magnetic induction compared to outside. And the other thing that can happen is that the macroscopic sample attracts the field line inside itself, and then we have a magnetic induction which is inside larger than outside. This kind of behavior is called a diamagnetic sample, and this kind of behavior is called a paramagnetic sample. We can look at this equation, that the magnetic induction inside is equal to the magnetic induction outside, plus something which comes in addition. And if the field is small, that B prime here, which comes in addition, is proportional to the induction outside. And the proportionality constant is called the magnetic susceptibility. Susceptibility is a Greek word. In German it means Aufnahmefähigkeit. I don't know it in English, sorry. It's susceptibility. And you see this here. A paramagnetic sample really likes to have the field lines inside. So the proportionality constant is positive, and in a diamagnetic sample, the proportionality constant is negative. And this is exactly the definition. If a macroscopic sample is called diamagnetic or paramagnetic, it is a sign of the magnetic susceptibility. So it's negative for a diamagnetic sample, and it's positive for a paramagnetic sample. You can also write it in a different way. This is B inside is equal to the magnetic field, and that what comes in addition is called M, demagnetization. And now there is a really big problem in magnetochemistry, and it's really a problem. When I was at university and had my physical chemistry classes, I was always asked and used to use only SI units. In magnetochemistry, there were two worlds, the SI units and the non-SI units. And I realized it not very early, but when I wrote my own script, when I really have to calculate numbers. Everything which is published normally is not in SI units. And therefore, this equation comes in very different forms. Sometimes there is a mu0 here, and the calculation back and forth between the CGS unit and the SI unit is not straightforward, because it's not only a power of 10 factor, there's sometimes a 4 pi, sometimes not 4 pi. It's really difficult. And if you really want to go into this, I found a very educational article, a review, from this year in the Journal of Radiation Chemistry from Mark Turnbull, who really reviews these problems, the historical things, and the relations between the unit systems. Okay, so what we need now is we need to measure from our macroscopic sample the magnetic susceptibility. When I was a PhD student and a diploma student, when the DCAT group was still in Bochum, we really had a Faraday balance. That was very cumbersome. It's really, it's the balance, and there is a magnet, and it's really, you are lucky and you get good data. Sometimes you have to repeat it, and you don't get good data. Then we moved to Mülheim, and Eckhard Bill joined our group from DCAT, and then we had a SQUID, and nowadays to get good magnetic data with a modern SQUID is really so nice. You can also, Frank Meyer said this, you can also measure the magnetic susceptibility with NMRs in solution. This technique is called the Evans method by a person who invented this. What you get out of from these measurements is we are chemists, so we want to have it in a molar unit. We get a molar susceptibility, and this means it's a measured one. This measured molar susceptibility always has two contributions. Because all matter has electrons, therefore we always have a diamagnetic contribution, which is small, but which is always there. But there are tables called Pascal's tables or Pascal constants, so you can calculate this diamagnetic contribution if you paint your molecule, and then what we normally do, we take the measured susceptibility and we subtract this diamagnetic contribution. Then we have only the paramagnetic contribution, which I term here chi-molar paramagnetic. But in the next slides, I skipped the paramagnetic because I always talk about the diamagnetic corrected susceptibility. So this is now the macroscopic world, and now we have to consider the paramagnetism on the microscopic, on the molecular world. And let us start with the molecule. This is a very simple molecule, very old one from the DCAT group. It's an octahedral iron 3 high spin compound with the Tecken ligand, and these are chloride ions. So this iron 3 high spin ion has a spin ground state of S of 5½ And this spin originates a magnetic moment of this molecule, and I picturize this whole molecule with a magnetic moment with this small sphere. This is what Frank Glaser yesterday said. This is a bare magnet. It has a magnetic moment, so it's a bare magnet. But we normally don't look at one molecule, so we always look at the condensed phase, in solution or in the solid state. And if we are in a solid state, we don't have one molecule, we have thousands, we have millions of molecules. So this is a very simple, pictorial way to symbolize the solid. Here we have our compounds, our iron 3 complexes. In between we have solvent molecules, or if we have ionic compounds, we have counter ions there. And this magnetic moment of this complex and its neighbor, they don't talk to each other. They are independent. That means that this magnetic moment and this magnetic moment, they are not correlated. There is no preferred orientation which is preferred. And that means now we have a sample which has 10 to the 20, 10 to the 22 molecules. And now we have these magnetic moments, and every direction has the same probability. So the magnetization of the sample, the magnetization, that was this in the macroscopic world, which comes in addition to the outside induction, is the sum, the vectorial sum of the microscopic, of the magnetic dipole moments divided by the volume. So if we now add the vectorial sum, all of these magnetic moments, where every direction has the same probability, what is the result of the summation? It's exactly 0. They cancel it out. It means we have, the physicists always say it, I don't like it, a magnetic molecule or a molecular magnet, but the sample has no magnetization. This is not a magnet like a piece of iron. It's a paramagnet. And without an external magnetic field, there is no magnetization. And now comes into play an external magnetic field. It is energetically more favorable that the magnetic moments align parallel to the external magnetic field. So now, if you have at low enough temperature and at high enough magnetic fields, now we orient our magnetic molecules, and if we now make a vectorial summation over this magnetic dipole moments, we come to a magnetization which is not 0. So with an applied magnetic field, we magnetize our samples of independent molecules. But the problem is, or the point is, if we switch off the magnetic field in a split second, that means 10 to the minus 6, 10 to the minus 9 seconds, they get randomized again. That means in this sample, we can magnetize it with an extramagnetic field, but if there's no field, there is no magnetization, it is not interesting for any magnetic applications. It's just a paramagnetic sample. And, as I said, this is an ensemble of independent particles because they don't talk to each other. So now we have the problem. We have the magnetic moment of a molecule, and we have the measured magnetic susceptibility of the paramagnetic sample, of the real macroscopic sample. And we have to relate these two things now. And this is again a very simplified picture from this. Now let's look at, we have 1 mole of molecules. I only take 8 directions of this 1 mole of molecules with these arrows. These are the magnetic dipole moments. If we have no magnetic field, all orientation are existing, and all of this orientation have the same energy. This is E0, means 0 field, 0 external magnetic field. And if we switch on now the external magnetic field, this is a very classical picture, and this is the classical energy of a magnetic dipole moment in the magnetic field. It's minus mu vector times h vector. This is a scalar product, so if you want to calculate a real number, because the energy is not a vector, it's a scalar, we have the magnitude of mu, the magnitude of h, times the cosinus of the angle in between. So now let's look at this magnetic moment of 1, which has an angle of 0 to the external magnetic field. So this magnetic moment becomes stabilized by this amount, minus mu times h. And if you look at this magnetic dipole moment, 2, it is a direction, this is an angle of 180 degrees. This is destabilized by plus mu times h. And now what we are doing is we make a Boltzmann population of these energy levels. And if you do this at any normal temperature, the energy levels, the lower energy levels are more populated than the higher energy levels. So what is the total energy of the system in the field? It's smaller compared to the zero field situation. A very important aspect is that for a paramagnetic sample, the total energy gets lowered by an external magnetic field. And this leads to a very important equation in magnetochemistry, how we can calculate the magnetization. The magnetization is nothing else than the derivative of the energy by the magnetic field. So if we stabilize something, then dE dH is negative. Negative times negative is positive. Then we have a positive magnetization, we have a paramagnetic sample. And this is also the reason, when we have an inhomogeneous magnetic field, that a paramagnetic sample gets attracted into the inhomogeneous magnetic field, because the highest energy stabilization is where the highest magnetic field is. So that was the classical picture. Now let's go to quantum mechanics. We have a molecule. A molecule has energy levels. So the N index here goes now over each energy level of the molecule. And we have to look at these energy levels in the presence of a magnetic field. And then, what is the magnetization for the macroscopic sample, which is the derivative of the energy of the field of the whole sample. Now we have a microscopic magnetization of each energy level, which is nothing else than the derivative, or the negative derivative of dE by dH. It means if the energy level of a molecule is independent of a magnetic field, it has no microscopic magnetization, no magnetic moment, and if we stabilize an energy level by increasing the magnetic field, it has a positive magnetic moment. So, and then it's a very important law. This comes now from statistical thermodynamics, because we have an independent ensemble of particles. We can take the simple partition function. So we can now relate the macroscopic magnetization which we measure to the microscopic magnetization of each energy level of 1 mole of molecules. And this is this partition function. Very important, there's no approximation. In the classroom I always call this the real equation, because there's no approximation. And I don't know, there's no name for it. And if you want to calculate now the susceptibility is nothing else than the derivative of the molar magnetization by the magnetic field. Usually what we are doing is we assume that the susceptibility is not dependent on the field, and then we can simply use the measured magnetization by the field. This is a source of a problem in the real world, because a slit magnetometer measures magnetization, not chi. The outcome of the slit is a magnetization, and we always use chi. So what we always do, which must not be correct every time, we divide it by the field of the measurement. And if there is something strange in chi, this is not because the sample is strange, it's because this assumption is then not valid. So if we have some magnetic ordering here, we have a very strange behavior of a field dependence, a very strange field dependence of chi. But this is because we do this very simple approximation, which is not always valid. Okay, this is the real equation, because I want to separate this from a very strong approximation. And the very strong approximation of this equation is the Van Vleck equation. The Van Vleck equation starts with an assumption that the energy levels of a molecule, these are these energy levels, can be assumed by a power series, independent of the magnetic field. So a power series is always a complete approximation, a good approximation, if the power series is infinite. But this would not be a simpler equation if we go to an infinite power series. So the Van Vleck equation stops at the square root dependence. So that's a very, very strong approximation. And then there is a very strong approximation, which is this here. The Van Vleck equation is only valid if the magnetic field is small compared to the temperature. So the Van Vleck equation is only valid if you go to high temperature measurements at low field. If we look at the magnetic properties at low temperatures and high field, you are not allowed to use the Van Vleck equation. People are always doing it, and then they become out some strange results. But it is because the approximation is not valid then. And if we then use this approximation, we get for the susceptibility this equation. This is the Van Vleck equation. You see the difference between the real equation, whereas there's no approximation. Here we have a derivative, and here we only need this constants. We don't need the derivative of the energies by the field. Okay, now let's apply this to calculate susceptibilities for special kind of ensembles. Let's start with a very simple ensemble. We have an ensemble of pure S equals 1/2 spins. Then we come to the Zeeman effect and then to the Curie, you will see. So the free electron spin is S equals 1/2, and you know that a spin of S equals 1/2 has two magnetic orientation quantum numbers, ms plus 1/2 and ms minus 1/2. The magnetic moment of these spins are not exactly collinear with the magnetic field, but they are preceding, I think it's not presiding, it's preceding, yeah? Precession. They make a precession around the field. And if we have the ms minus 1/2 quantum number, then the magnetic moment is orientated not directly but in the way of the magnetic field. And if we have the ms of plus 1/2, it is in the other direction. I use here the magnetic moment because the magnetic moment is always the same. The magnetic moment of an electron and the magnetic moment of a nuclei. They always want to be parallel to the magnetic field. The electron spin is in the other direction. Yeah, so the electron spin and the magnetic moment are pointing to different directions due to the negative charge of the electron. If you go to nuclear spins, they have positive, so the nuclear spin and the nuclear magnetic moment are in the same direction. For the electron spin, it's not. So they make a precession, and therefore we have determined the length of this vector, and we have determined the projection of this vector onto the magnetic axis, which is the quantization axis, it's the z-axis, and because it makes a precession, the x and y direction is not determined. And we can calculate now the energies of this S equals 1/2 system using the Zeeman effect. This is the Hamilton operator for the Zeeman effect. So it is a Bohr magneton, which is only natural constants. This is the famous G value. This is for me the G value. It is defined by this equation. We don't know now the value of it. This is the magnetic field, and this is the SZ operator. And this Hamilton, the spin Hamiltonian, as Eckart introduced earlier, this operates on spin wave functions. And it took me a long while to understand what is a spin wave function. We always use, in the training as a chemist, orbitals. An orbital is something we can write down the wave function. There are exponential terms, there are cosines, sines, all this stuff. There is no analytical equation for a spin wave function. This is very difficult to realize. You have to realize. There are two equations which define a spin wave function. And these are these two equations. This is a spin wave function. It is classified by the spin quantum number S and its orientation quantum number ms. And this is the definition of a spin wave function. The SZ operator applied on SMS leads to the same spin wave function, and the ms wave spin quantum number is written in front. And the other direction is S squared, working on SMS. Then we again get the same spin quantum number, and in front we have to write down S plus 1. And this is exactly what is written here, that SZ and S squared is determined, but SX and SY is not determined. Then you have to use the ladder operators which were introduced by Eckart in the morning. And for this lecture, I always want to be very accurate in my writing. This is a not bold italics S. That means it's a spin quantum number. If I use a not italic but a bold value, it is a spin vector. And if I use this Dach, what? Oh, okay, then it's operator. Yeah. So S can be a spin quantum number, a spin vector, and a spin operator. So, and as Eckart explained to you, we have now two wave functions, two spin wave functions, classified always by S, ms. So this is for our system, S equals 1/2, ms plus 1/2. And now we have to do our quantum mechanics. We have to solve the Schrödinger equation. And it's nice, we can do it on a piece of paper, it's very simple. So this is our operator, or Hamiltonian, working on 1/2, 1/2. Means we have to write down the ms in front, this stays there, and we keep our wave function. So we have solved the Schrödinger equation. H on the wave function gives the energy times the wave function. So this is now the energy of this state in the magnetic field. The energy of the ms plus 1/2 is 1/2 μB Gb. So the μB is only natural constants, the B is the magnetic field, and the slope, which is now what is characteristic for our sample, is a G-value. We have no clue at the moment what the G-value will be. Now we do the same thing for the second state, which has the wave function S equals plus 1/2 and ms equals minus 1/2. We do our quantum mechanics, we solve the Schrödinger equation. I think it's great. This operator working on the wave function, we have to, this SZ operator means we have to write down the ms in front. We do it here. So it's operator times wave function, it gives the energy times the wave function. So the energy of this state is now what's written here. It is minus 1/2 μB Gb. And we can picturize it now in an energy diagram. Our S equals 1/2 system is degenerate if we have no applied magnetic field. And if we now apply the magnetic field, the ms minus 1/2 gets stabilized and the ms plus 1/2 gets destabilized. And these are the energies. These are the energies from the quantum mechanics. And now comes something which is very interesting. We relate this to the classical expression. The classical expression was the energy of a magnetic moment in a magnetic field. It was 2 or 3 slides before. It is minus mu times B. So now we can equate these 2 equations, and what comes out is that the magnetic moment of, and it's very important, it's the magnetic moment of this ms sublevel is 1/2 times G times mu B. And the magnetic moment, the microscopic magnetization of this sublevel ms plus 1/2 is minus 1/2 G times mu B. So if you have a free electron, you have a G value of 2.0023, let us assume it's 2.0. That means that the magnetic moment of this energy level is 1 Bohr magneton, just 2 times 1/2 is 1, yeah? And the magnetic moment of this ms plus 1/2 level is minus 1 magneton, Bohr magneton. We have now everything we need to calculate the magnetic magnetization for this ensemble of spin 1/2 systems. This was spin 1/2. If we have it now for a general spin, s equals 1, 3/2, 2, 5/2, the equation from the Zeeman effect is like this: ms times mu b times k times the magnetic field. And the lowest level has a magnetic moment of minus ms g times mu b. So if we have a 5/2 spin, the lowest level will be the ms minus 5/2. Minus times minus 5/2 is 5/2, and then times 2 is 5. So the energy level at the lowest, the ms minus 1 has a magnetic moment of 5 Bohr magnetons. This is our equation now, and we can plug in this equation in the van Vleet equation. That was the equation for the approximate equation, for which we can calculate the macroscopic magnetic magnetization if we know the energy levels of our system. We know the energy levels of our system. If you plug this in, what comes out is the Curie expression. So the Curie expression arises if we have a spin, a pure spin, no d, only spin, and we use the approximation of the van Vleet equation. That means the Curie law is only an approximation. It is only valid at a ratio that the magnetic field is small and the temperature is high. The Curie law is not valid if we go to low temperature and strong magnetic fields. So chi is equals to the Curie constant divided by T. And from the calculations, the Curie constant is exactly defined by these numbers. And now comes something very important. And I repeat this in my classes all the time. We can just rearrange this equation to this. Yeah, I take this equation, I rearrange this, and then I call this term the effective magnetic moment. The effective magnetic moment is nothing else than a rewriting of the Curie law. And this relates now, that is really, I love the effective magnetic moment, because it's relate a measured quantity chi to theory, to the spin quantum number and to the G value. And now comes a big problem, always. There are 2 quantities, they almost look the same, they always have the same name. This is a magnetic moment, and this is the effective magnetic moment. And these are 2 complete different quantities. The magnetic moment I have here is the magnetic moment of 1 ms substate. The effective magnetic moment is a Boltzmann weighted ensemble value for all molecules. These are completely different things. So for a spin of S equals 1/2, this substate has a magnetic moment of 1 Bohr magneton. Sorry. But the effective magnetic moment, you all know, for a spin of 1/2 is 1.73 Bohr magnetons. There's nothing wrong. These are two completely different things. So now we can make a graphical presentation for our system, a spin of 1/2, and as we see, the Curie law says that the molar susceptibility is inversely proportional to the temperature. The solid state chemists always make this kind of presentation. I don't like it because I don't see anything from this. I just have to make a simulation to get something out. Sometimes the solid state chemists use this kind of presentation, so it's 1 divided by chi versus t. So it's a straight line, but again, to get something else, I need to get the slope. So the molecular chemists like one of these two representations. Because now, if I make chi m times t versus t, I have a straight line with no slope, and I can directly see from the y-interception a value, which is now a characteristic for my system. And you can also use the mu effective. They also have the same kind of behavior, because mu effective is nothing else than 2.828 times the square root of chi mt. So. Again, there are two families in the molecular magnetism community. One family really says that you have to use mu effective, and the other family you say you have to use chi mt. There is nothing wrong to use this or that. But the IUPAC says use this, use mu effective. Because there is one really big thing about mu effective. It's independent of the unit system, SI or CGS. You see, here's chi. Chi is dependent, the value of chi is dependent on the system, SI or CGS unit system. If you use the effective magnetic moment, it's independent on the system you use. So therefore, you can simply compare your values. Okay, this is a Curie law, and I told you it's an approximation. It's an approximation because it is based on the Van Vleck equation. So if we now use our Curie law and we want to magnetize it, so magnetization is just chi times the field. So we have the Curie constant, we have the field, and we have the temperature. From this equation, the Curie law tells us we can magnetize our sample as high as we want. We just have to go to high fields. We can even magnetize it more and more because we can increase the field more and more, or we can decrease the temperature, and that means also that the magnetization can be indefinitely high. But this is not possible because this is only an approximation. And at this, at high field and small temperatures, it is simply not valid. So what happens now if we really go to low temperatures and high magnetic fields? Let us assume we have a general spin S, then we have the energy levels, and the lowest energy level will be the ms equals minus S. If we have 5 then the lowest energy level is ms minus 5 half. Then this lowest energy level has a microscopic magnetization and magnetic moment of minus ms times g times mu b. And if we have now all molecules in this state, then the magnetization is the sum of these microscopic magnetizations divided by the volume. But this is a value which cannot be increased. This is the highest magnetization value which can be achieved in a real system. And therefore, this is completely nonsense what the Curie law is telling us here, because it's not valid. That means we have a saturation magnetization. And that means that 1 mole of our sample, of our molecules, are now in this lowest energy level, and therefore we can simply calculate the saturation magnetization. It's minus the Avogadro constant, the MS level of the lowest multiplet level, the G value and μ. If we take into account the saturation effects, we have to calculate, or we have to get to a new equation. We got to the Curie law by plugging the energy of our S equals something, our Zeeman law, into the Black equation. So we don't want to have an approximation, so we have to plug it now into the real equation, as I call it all the time. This is the partition function without approximation. So we have our energy levels, I plugged it in, and now you can do some mathematics. I have to admit I never did it. I have no clue how to come to it, but I don't need to, I just use it. This is now our no approximation, our molar magnetization. We have a vector in front, which is nothing else than our saturation magnetization times the so-called Briand function. The Briand function is written down here, and the argument x of the Briand function is the ratio of magnetic field to the temperature. Very important. If this argument of the Briand function goes to infinite, the Briand function goes to 1. That means if we go to high field and small temperatures, we have this as 1, so we come exactly to our saturation magnetization. And if this goes to 0, the Briand function goes to 0. And this is shown here for spin of 1/2, spin of 1, spin of 3/2, spin of 2, spin of 5/2. On the y-axis, I've written the molar magnetization divided by Na, G, and B. And here is the argument of the Briand function, which is the energy of the magnetic field divided by the energy of the temperature. And you see here, at low values of this argument, we have linear dependence. This is where the Curie law approximation is valid, because we have low field, high temperatures. And if we go to high values, we come to our saturation magnetization. And the nice thing about this kind of graphical drawing is that the value on the y-axis gives you exactly the spin state. So for 5/2 you get to 2.5. So this was now a system where we have an isotropic spin. But normally we don't have, and we don't want to have, an isotropic spin, and therefore we have to talk now about the zero splitting, which is very simple now because Eckart did a good introduction. So a spin of 5/2 can be split by zero splitting into Kramers doublets. They can be in this order if the parameter of the zero splitting is negative d, then the plus minus 5/2 is lowest in energy, then the 3/2 and the plus minus 1/2. And if the d value is positive, the splitting is reversed. And this is the zero field spin Hamiltonian, which was introduced by Eckart in the morning. Let us calculate this now for a model system of S equals 5/2 with no rhombicity. The E was a rhombicity, which means that the X and the Y direction are different. So let us assume we have axial symmetry, so we want the D value and E 0. And we want to calculate it also in a magnetic field. And this is very nice for me, I don't have to explain this, because that was nicely introduced by Eckart. So we have now the Zeeman term in X direction, Y direction, Z direction, and our axial zero splitting. And this now acts on our spin wave function, and if we have 5/2, S equals 5/2, we have M as plus 5 half, plus 3 half, plus 1 half, minus 1 half, minus 3 half, and minus 5 half. And this is now our matrix, our spin Hamiltonian matrix for this system. Our wave functions are now written only by the ms value, 5 half, 3 half, 1 half, minus 1 half, minus 3 half, minus 5 half. And we obtain this matrix elements. How you get it? We have learned it in the morning. We assume now that we have a large zero splitting and only a small magnetic field. And if you look at the 5 half and the minus 5 half quantum numbers, they are starting in zero field at the same energy. 10 divided by 3d, 10 divided by 3d. And the plus 3 half and minus 3 half also has the same energy in zero field, minus 2/3 d. And also the plus minus 1 half starts with the same energy. This is what is written here. And therefore I know the energy difference between the states. Now we can rearrange this matrix. I want to rearrange it in a way that the wave function, which has the same energy in zero field, means hx, hy, hz is 0, are close together. There is no strange things here. I just rearrange it. 5 half and minus 5 half have the same energy in zero field. 3 half and minus 3 half have the same energy in zero field, and the same for plus minus 1 half. But I made it more simple, because I have the approximation that I am in a strong zero field splitting regime and a small Seeman's effect. And therefore I say that the energy splitting between 5 half and 3 half is large. And therefore the interaction between this is small. The interaction between two wave functions is always small if the energy separation is large. And as the d is large compared to the mixing elements from the Seemann effect, I can skip it. This is an approximation. And now I look at the ms plus minus 5 half Kramer doublet. So I just take this block of the matrix. What do I see here? There is in the diagonal our energy, 10 divided by 3d, and now comes the Seemann effect in z direction. So let us assume we have now this Kramer's doublet at zero field, and now we apply a magnetic field in the z direction. We get an opening. As we have seen the whole day. The minus 5 half is stabilized by this amount, by this amount, and the plus 5 half is destabilized by this amount. That means we have an energy of the minus 5 half state which is lowered. That means this state has a microscopic magnetization, because the microscopic magnetization is a negative derivative of the energy by the field. So we have a magnetization in z direction. Now let's put in a magnetic field in x direction or in y direction. In this part of the Hamilton matrix there is no hx or hy. So hx and hy has no effect on this Kramer's doublet. That means if I start in zero field and I use now the field in this direction, there is no splitting. The energy of this plus minus 5 half is independent of the magnetic field in x and y direction. It has no magnetization. That means that my plus minus 5 half doublet is anisotropic. Anisotropy means different behavior in different direction of space. This is, as Eckert introduced, an easy axis of magnetization. If we go to the z direction, we can simply and easily magnetize it, where there is no magnetization at all in x and y direction. So if we have a negative zero splitting with the plus minus 5 half at the bottom, we have an easy axis system. And this is why people always say that zero field splitting describes magnetic anisotropy. It is wrong saying the other thing. D, or zero splitting, is not the magnetic anisotropy. But D describes one sort of magnetic anisotropy. Okay, how can we determine D? So we can determine D very good with EPR, which will be discussed tomorrow. I talk about magnetization measurements. I have plotted here my magnetization versus this B divided by temperature for a spin of 5½ I assume a G value of 2. If I have no zero splitting, D equals 0, I have this light line, and this exactly corresponds to our Brion function 2 or 3 slides earlier. And now if I calculate this, really by doing what Eckert was saying, the diagonalization of the matrix, and calculate it for a D of +1 or D of +3, you see the saturation magnetization is smaller. It does not saturate at 5½ times NAG mu B. It saturates at a smaller value. So this is how we can extract from such kind of magnetization measurement the D value. We can fit our spin Hamiltonian to the experimental data. And it's very difficult to understand why is the magnetization, the saturation magnetization smaller if we have a D. Because we always think in the Z direction. The other saturation magnetization is the same. But as Eckert was showing in his nice diagrams, the magnetization in X and Y direction is smaller. And as we have a powder, so we have to look at all directions, the saturation magnetization for the powder system is smaller. What we are normally doing is so-called VTVH measurements, so we change the field and the temperature. And that's historical here from Mülheim, we use 1, 4, and 7 Tesla. And if there is no D, then we have for each field the Brion behavior, and this means that our ISO field lines are completely superimposed. If we have now a zero splitting, and I calculated for plus and minus 2 wave numbers, we have a nesting behavior of the isotopic lines. And the nesting behavior of the splitting of these isotopic lines will be stronger, the stronger the absolute value of D is. You see here the difference between plus and minus 2 wave numbers. What is normally said in textbooks or in scientific papers is that from a powder measurement you cannot obtain the sign of D. Yes, that's correct. But in some special cases you can be lucky. And you see there's a small difference. Well, it will be difficult to really say that this is from a measurement you can really decide a plus or minus. But in some cases you are lucky and you really can obtain the sign from these VTVH measurements. So that is now also what we see now from the spin Hamiltonian, that there's a little splitting. But now comes the question, where comes this D from? So in the whole week you will learn a lot of sophisticated ab initio and DFT methods, how to calculate D in a way that you can calculate it, but it's far away that I can understand it, where it comes from. And this is what Glaser was saying, the simple way to understand the origin of D is ligand field theory. It is simple, but it's understandable. So if we look at the case of an octahedral nickel-2, then we have, in the real octahedral case, the triplet A to G is ground state, and as 10 dq above, we have the triplet T to G state. This triplet A to G ground state is magnetically completely isotropic. To understand the origin of the anisotropy and the zero splitting in nickel-2, which is famous for a strong V value, is that we have to combine the effect of spin orbit coupling and symmetry lowering. So if we now use the Hamiltonians describing the spin orbit coupling and the lowering from OH symmetry to T4H symmetry, then this triplet A to G ground state splits into a component which can be described by M as equals 0 and a component which can be described by plus minus 1. And the energy difference is zero splitting. In ligand field theory, that gives you a very simple equation for D. And this is a simple equation for D. So you see this lambda is the spin orbit coupling constant. That means if you go in the periodic table more down, the spin orbit coupling constant gets larger, so the D gets larger. And then you see it is directly dependent on delta. Delta is the splitting of the exciting state due to the symmetry lowering. That means if we lower the symmetry more dramatically, the delta gets stronger and therefore the D gets stronger. So geometrical distortion is good. And this is also is not very intuitive, but it's very important. Yeah? The larger 10dq, the smaller D. Because the spin orbit coupling mixes this state into the ground state. And the mixing is always more efficient if the energy difference is small. So if you have a small 10dq, this state comes down and it's more efficiently mixed in. So if you want to increase D, you have to use pi donating ligands and not pi accepting ligands, for example. So that was everything on mononuclear complexes. Let's now come to exchange couples, polynuclear complexes. This is again a very old compound of the Vika group. It is a dinuclear iron 3 oxo iron 3 complex, 2 carboxylates, and here's again the second ligand. So here we have a magnetic moment in the spin, here we have a magnetic moment in the spin, and quantum mechanics tells us if they are talking to each other, and now they are in close distance, and they are bridged by a common bridging ligand. If they are talking to each other, then the orientation of the spins and magnetic moments are not independent anymore. They can only have this orientation, one is up and one is down. They are anti-parallel. This coupling is called anti-ferroelectric coupling. And if you have 5 in this direction and 5 in this direction, the ground state is S equals 0. Or they can be ferroelectric coupled. That means they are parallel. Then the ground state is 5 plus 5, it is 5. And now comes a figure which is not possible for this case. I just want to show you. This is only an example. Doesn't relate to this. For example, if we have iron 3 nickel 2 dimer, and the coupling is anti-parallel, we have 5 in this direction and 1 in this direction. 5 minus 1 is 3 So we have an anti-ferroelectric coupling, but the ground state is not 0. There is something left over, and this is called a ferrimagnetic coupling. So for the case that we have a ferroelectric coupling, is it a ferromagnet? Simple question, very important question, because 80% of literature, they always mix these two things. It is not a ferromagnet, because this is a molecule. In the solid state again, we have our ferromagnetically coupled dimer, but this dimer is not interacting with the other dimers because there are solvent molecules in between, there's organic stuff around. So they are still simple paramagnets. But the units are not mononuclear complexes, but they are coupled dinuclear complexes. So a ferromagnetic coupling does not mean it's a ferromagnet. It's very important to differentiate here. Okay, how can we describe this coupling? This is the famous Heisenberg-Dirac-Van Vleck exchange Hamiltonian. And again, very important, this is a J written in italics. This is a coupling constant. It gives you the magnitude of the coupling. And these are not italic, but bold, as these are spin vectors. And there should be a roof on top because they are spin vector operators. So in the literature, there are now, I have found four different definitions. I define it always, because I come from the Wiener family, and they always do it like this, minus 2j S1 S2. But you can find also minus j S1 S2, you can find plus j S1 S2, and you can find plus 2j S1 S2. The physics is the same, but the j values which comes out, they are different. So therefore it's very important, if you publish a paper and you calculate j, either by theory or you extract it from experiment, you always have to write down the Hamiltonian you use. So in my representation, if you have now a negative j, this corresponds to the anti-Faraday coupling, and if you go to a positive j, we are in the Faraday coupling regime. So if we now couple two spins, we get a total spin, and we cannot only look at the ground state, but also have to look at the exciting states. And how to calculate the possible spin quantum numbers for the total spin. It's very important, but ST means it is a coupled total spin of the dinuclear unit. And S1, S2 are also local spin quantum numbers. So the maximum spin quantum number is to just say S1 plus S2, and the lowest value is the absolute value of the difference. That means if you have iron 3, 5 what did you get? You don't get minus 5. Yeah? Because 5 plus 5 is 5. 5 minus 5 is 0. So everything between 5 and 0, so 5, 4, 3, 2, 1. There is no possibility for a negative spin quantum number. It doesn't exist. So now we want to solve this Hamilton operator. We want to solve the Schrödinger equation for this Hamilton operator. And again, we don't need a computer, because this is again something which we can write on a piece of paper. And how can we do it? Well, these are the spin quantum numbers, but this is now the vectorial representation. The total spin is a vectorial sum of the two local spins. So we can square this equation. So we have ST squared plus in brackets S1 plus S2 squared. We can get rid of our bracket. So we have S1 squared plus S2 squared plus 2 times S1 S2. We have this expression which we need here. So we can rearrange this to S1 S2 and can plug this then in to here. And remember, what is the definition of a spin wave function? The action of the S squared operator on S brings you S again, and here are now spin quantum numbers. You just have to write the spin quantum number here in front of it, S plus 1. So this is our spin Hamiltonian now rewritten, and now we can simply calculate this by applying on the spin wave function. The spin wave function I've written in this form, that I have 3 quantum numbers which characterize my spin wave function now. It is the quantum number for the total spin and the quantum numbers of the two local spins. And just if you now apply this, you come to the energy, and the energy is this equation. This equation, this energy is dependent on the total spin quantum number and the S1 and S2 quantum numbers. Very, very important equation. And this is now picturized for a copper dimer, for example. Spin 1 is 1/2, spin 2 is 1/2, and we assume that the coupling is, as it is always in 99% of the cases, anti-ferromagnetic. So we have an S equals 0 ground state. The energy of this you can simply calculate. Plug in for ST 0, for S1 1/2, for S2 1/2, and the energy of the state is plus 3/2 times J. And the same we can do for the exciting state. The ST equals 1. Plug in a 1, a 1/2, a 1/2, and you come to an energy of minus 1/2 times J. And you see the energy difference is 2 times J, and because we are antiferromagnetic here, the J is negative, so this is lower energy compared to this, because this is a positive energy, because J is negative. I have now calculated this, and because this equation can now be used into our real equation to calculate the molar susceptibility. We can calculate chi, and we can calculate mu, because we have the energy for our system. And this is now the result. So if there is no coupling, J is equal to 0, we have the behavior, the Curie-like behavior. No temperature dependence of mu effective with the temperature. If we have an anti-ferromagnetic coupling, so we have a negative J value, you see mu effective decreases with decrease in temperature. And if we are at 0 Kelvin, we only have this state populated in S equals 0. S equals 0 has no moment, and therefore we go to 0. And if we go now here with a ferromagnetic coupling, then we have this state as a ground state, so we have to think reverse. And at low temperature, only this state is populated for a positive J. And I used for copper 2 a G value of 2.11, and then if you have an S equals 1 with G of 2.11, you come to 3 Borsche magnetons. This is how I prefer the drawing of this data. You see, this is the solid state chemists' drawing. They use chi m versus T. And you see, if it's uncoupled or thermally coupled, you cannot even have a qualitative look at this. It looks the same. You cannot distinguish. But in this kind of drawing, you can simply distinguish between uncoupled, anti-ferromagnetic, and ferromagnetic coupling. So let us use our system of iron 3. We have spin of 1 and 5½ on both sides. The total spin, as we have seen before, can have values from 5, 4, 3, 2, 1, 0. And you can now calculate the energies of these S total states by this equation. And this equation is simplified because I have done something. I have skipped this. Because for one dimer, this is always the same contribution. So it only shifts the point of 0. It doesn't matter for the energy differences. We only need energy differences. And therefore, I just use this term with ST. These are the values for the spin states, and this provides us our spin ladder for a 5½ anti-ferromagnetic coupled system. As again, in 99.999% it's anti-ferromagnetic, so the J value is 0, and we have an S equals 0 ground state. And now comes the S equals 1. The energy difference is again 2J between these two, but the energy difference increases with larger S value. And now again, we have, if we make a magnetic measurement at 0 Kelvin, only this state is populated. And then if you increase the temperature, we have a Boltzmann population of all spin levels, and this can be done with our real equation, the partition function, and therefore we can calculate for our iron 3, oxo iron 3 dimer some values, which is written here. This is if you have an uncoupled system. It's again Curie-like with no temperature dependence of mu effective. And then if you have an coupling, you see the stronger the coupling, the lower the value of mu effective. And if you have a strong coupling, minus 200 wave number for example, that means that this energy difference is 400 wave numbers. The energy at room temperature is equal to 200 wave numbers. It means we need some temperature to have even a small Boltzmann dependent occupation of the first excited levels. You see here that it's just the strong energy differences between these energy levels that you get such a small value of mu effective here. What can we learn from this? Well, we can simply make a structural argument. Because if you have an O2 bridge and an O2 minus bridge, then the coupling between two iron 3 ions is mainly in the region of -100 wave numbers. For the definition of the Hamiltonian, -2JS1S2. If we have an OH bridge, the coupling is smaller. Why it is smaller? Just in a moment. Of only -10 wave numbers, and if you have a water bridge, it's close to uncoupled. So this comes from the measurement. And now we want to understand the covalency of the metal-ligand bond, which we can measure with these values. So now comes the super exchange mechanism. Where comes this coupling from? And I want to start with some very, very important considerations. Interaction between periodic centers. There are two completely different pathways. There's one pathway through space. Yeah? Our one magnetic ion has a magnetic moment, has magnetic field lines. Our second magnetic ion has a magnetic moment, has magnetic field lines. And these magnetic field lines, the magnetic dipoles, can interact. This is a real magnetic interaction. It's called the dipolar spin interaction. But this mainly is, normally is very small. It's for normal distances between periodic centers, smaller than 1 wave numbers. So we don't take this into consideration. Yeah? Through space, this is a dipolar, it's a magnetic interaction. So we only think about interaction through bonds. And this is an electrostatic interaction. This is not a magnetic interaction. This is a large contribution to the J value. You see it can be quite strong. So it's always difficult if you read a paper or you go to a talk and the people are talking about magnetic interactions. Normally they don't mean it because there are always electrostatic interactions. But you have to think about it. You can even subdivide this through bond interactions to direct exchange. This means if the d orbitals, where the electrons are directly interacting, there's a metal-metal bonding, but that is not what we normally have. We normally have the so-called super exchange. That means that the d orbitals, where the electrons are interacting with the orbitals of a common bridging ligand. And this is called super exchange. So I want to explain to you a very simple model, but which is very intuitive for the chemist, and this comes from Olivier Kahn. I hope in the later talks there will also be the Anderson model, and there will also be some more sophisticated models. This is a very simple model for chemists. And that is of one of the fathers of molecular magnetism, of Olivier Kahn. So if you have a model system, you have two magnetic ions and you have a bridging unit. The first thing what Olivier Kahn did is something completely stupid because it cannot be done. It's just in the Gedanken experiment. He cleaved it into two units. And for these two units now, we can simply use simple, not using order calculation, just simple textbook-like molecular orbital arguments. We have a transition metal, we have a ligand, we can picturize the molecular orbital on each side. And Olivier Kahn called this the natural magnetic orbitals. A magnetic orbital is an orbital where only one electron is in. If you have a double occupied orbital, it's not a magnetic orbital. If it's not occupied, it's also not a magnetic orbital. A magnetic orbital is only one electron inside. And let us assume a simple copper-2 system. And we have here some bridging ligand, like a hydroxide, for example. Then we can simply think that our copper-2 is a D9 system, square planar, so the magnetic orbital is a dx squared minus y squared orbital, pointing directly to the ligands, and there will be some kind of pi orbital on the ligand which makes a sigma bond to the d orbital. Also there will be some contribution, but it's not important now for the super exchange mechanism. So this is the natural magnetic orbital on fragment A. This is the natural magnetic orbital on fragment B. And the idea of Olivier Kahn was that exchange coupling is a sort of weak chemical bonding. And chemical bonding is always picturized for the chemists that two binding partners approach each other. Like if you make from two H atoms, H2. And that's the same thing what Olivier Kahn is doing here. So the two fragments are coming together. And you see here, now you get molecular orbitals. And this was the bonding MO. And if you do now the theory, which is written down very nice in Olivier Kahn's textbook, you come from this simple picture to an expression for the exchange coupling constant. So this J is the exchange coupling constant. And the exchange coupling constant has two contributions. It has a contribution by a capital K. The capital K is that what Frank Nese introduced yesterday. It is the exchange integral. There is no exchange interaction, there's just electrostatic interaction, and this is the exchange integral. So the exchange integral is an integral between two electron densities, even if they are exchanged. Very strange to understand, but if that's electron densities, it's electrostatic interaction, it's a repulsion, and therefore this exchange integral is always ferromagnetic, is always positive. That means the exchange integral always gives you the ferromagnetic contribution to the coupling constant. You can imagine that you know Hund's rule for the atom, where the exchange integral always gives you the high spin state. Hund's rule said the high spin is always stabilized. That means this is something like Hund's rule in a molecule. The exchange integral always stabilizes the highest spin, so it's a ferromagnetic coupling contribution. And then there's a second term, 2 beta S. Beta is a resonance integral describing the bonding between the metal d orbital and the ligand orbital. So this is something which quantifies the extent of the metal ligand bonding, of the covalency. And now I'm not responsible for this. There is an S. It is not the spin. The theory doesn't have enough letters. Thank you. This is the overlap integral. It is the overlap integral between the two natural magnetic orbitals. So this contribution is always anti-ferromagnetic because beta and S have always opposite sign. So now let us look at our situation for a copper dimer. So in the uncoupled, far away, we have our natural magnetic orbitals, A and B, each carrying the one electron of copper 2. And now we make the bonding between the natural magnetic orbitals. We get a bonding situation and an anti-bonding situation. And now we have to put into the molecular orbitals here, for the dimer, the electrons. Well, the first is easily put into the lowest one. But where do we have to put the second electron in? We can put it with Pauli principle, with opposite spin in the lowest bonding orbital, or we can put it with parallel spin into the higher orbital. Well, this is now really what comes from this equation. We always have both contributions. K always favors this configuration. Why this term always favors this configuration. So, the stronger the metal ligand bond, the larger is the resonance integral beta, and the larger is the anti-ferromagnetic contribution. Because this is always negative, because beta is always of different sign to S. So the J value gives us a quantitative thing about the metal ligand covalency. That's very, very nice. And, very important, if the magnetic orbitals are orthogonal, then the overlap integral is 0. And if this is 0, the antiferromagnetic contribution is 0. And then only the contribution from the exchange integral is there, which is ferromagnetic. That means if we have orthogonal magnetic orbitals, then we have always a ferromagnetic contribution. This is the explanation of Olympic Kahn. The same results already arise from the solid state physicists. That was Anderson and Goodenough and Kanamori. And these are the so-called Goodenough-Kanamori rules, which are a recipe for us, for the synthetic chemist, how to create, to design ferromagnetic or antiferromagnetic interactions. So the first Goodenough-Kanamori rule says, if two magnetic orbitals interact and the overlap integral is not 0, the interaction is antiferromagnetic. And this is normally 99.9% always the case. The interaction is ferromagnetic if the overlapping magnetic orbitals are orthogonal to each other. Then the overlap integral is 0 and the interaction is ferromagnetic. Only the K is there. And then there's a third one, more difficult, the non-orthogonal overlap of a magnetic orbital of one metal center with a filled or empty orbital on the other metal center yields also a ferromagnetic interaction. If you want to understand this, come after this lecture to me and I explain to you. So these recipes have been applied to a very, very famous class of compounds by Hatfield and Hodgson, which came to the first experimental magnetostructural correlation. We look at dimeric copper compounds, copper 2, with a bidentate nitrogen ligand. So here is a list. All of these compounds have this kind of structural motif. And it doesn't matter what the names of the ligands mean, because they are simply bidentate nitrogen donor ligands. And here, this is the measured exchange coupling constant. Wow. It varies from very strong ferromagnetic to even more strong antiferromagnetic, with the same structural unit. And look at this. This is a compound with some kind of ligand and perchlorate as a counterion. And this is the same compound. It just crystallized in a different form. There's the same composition, just two different crystal structures, therefore called alpha and beta. This is almost not coupled, and this is strongly antiferromagnetic coupled. So how to explain this? And Hatfield and Hodgson simply realized that there is a correlation between the coupling constant and this angle, copper, oxygen, copper, alpha. It's written here. And here I have used Excel just to make a correlation. This is the experimentally determined J value, and this is this angle alpha. And you see there's a very well defined linear correlation. And if you have an angle which is around 0.5 degree, you have a coupling of 0. If you have a larger angle, you have an antiferromagnetic coupling. And if you have a smaller angle, you have a ferromagnetic coupling. This is the fit I have in the red line. How to understand this? Well, we can simply understand this with our Goodenough-Kanamori rules, or with the Kahn theory. If we are at an angle of 90 degrees, then the p orbitals at the oxygen are orthogonal to each other. Therefore, the magnetic orbitals, the natural magnetic orbitals, are orthogonal to each other. That means S is 0, the overlap integral. Then the 2 beta S term is 0, and our coupling constant is just the positive exchange integral. And if we now reduce the angle from 90 degrees to something higher, if we increase the angle, then this term increases, and therefore this term is stronger, and at the magic angle of 97.5, those contributions are there, but they are of the same absolute value. And therefore the observed coupling constant is 0, but they are coupled. But the coupling constant is 0. Very difficult to understand. Yeah, and this, okay. Olivier Kahn, he was a very strong person with very strong opinions. He said to this example, accidental orthogonality. Accidental. Because look at this. You have the same compound just crystallizing in different space groups, and you have completely different angles and therefore different coupling constants. You cannot control it. But if you want to design something, you need a control. And opposite to this accidental orthogonality is the so-called topological orthogonality. And this is an example from our group with this ultra simple ligand. So we have done two compounds. We have done a copper 2 compound and a copper 2 vanadyl, vanadium 4 compound. If you look at the magnetic orbitals for the copper 2 case, we know copper 2 is a D9 system in a square planar environment. The magnetic orbital is the dx squared minus y squared orbitals pointing to the ligands. And the angle here, copper, oxide copper, it is not 90 degrees, it is something like 115 degrees. So it's a strong antiferromagnetic coupling regime. So we can simply say, before we measure it, this must be antiferromagnetic coupling. Now we go to the copper 2 vanadyl 4 case. Vanadium 4 is a D1 system. This is an oxo ligand which is in the Z direction. This is a quantization actually, because this is a very strong, two negative charges at a very short distance. So all orbitals with the Z component are destabilized. That means in our T2G subset for octahedral symmetry, the dxy is lowest in energy and dxz and dyz is increased in energy. Therefore the D1, the one electron is in the dxy orbital. This is this one. And you see, these two orbitals are orthogonal. And they are always orthogonal, irrespective of the angle. That means we can say the overlap integral is always 0, not the spin. Yeah, this is the overlap integral. And therefore, the coupling should be ferromagnetic. So that was the thinking, and now go to the measurement. You see, this is the measurement for the copper 2 compound. A decrease of mu effective with decrease in temperature. The solid is a simulation, which is based on the HDVV Hamiltonian and on the real equation for the calculation of the molar magnetization for the macroscopic sample. And the J value is minus 374, very strong antiferromagnetic. And this is the measurement for the copper 2 vanadyl case. And you see, mu effective increases with decrease in temperature. You simply see qualitatively it is ferromagnetic, and if you now simulate the data, comes out as a J value of plus 40, so it's ferromagnetic. You see, the good enough Cannon-Mori rules are now really good recipes for us, for the synthetic chemist, to design molecules with ferromagnetic actions. And this is what we want. If we now go to the other side of the first slide, if we go from the simple molecular magnetism to the application, because we want to make molecule-based magnets, and this is something which I would talk if I would make a scientific lecture, but not today. Today I've only covered the basics, and if you have any questions, you can ask me now, you can ask me later, whatever you want. Thank you for your attention.